which we have left yesterday, the Advanced Computer Architecture, Unit 3 of the Lecture 2. But before going to start with the session, my once again the appeal to all of you people to prevent the COVID-19. Stay home, stay safe. Wash your hand for at least 20 seconds up with soap whenever you use or you for any purpose. Okay, now we start with our topic, that is yours is the 2D mesh. It is one of the most popular topology used in computer architecture. It is also called two-dimensional hypercube. The wonderful thing about this, it represents a good compromise among the contradictory requirements of various network parameters as shown below. The diameter, the parameter d, that will be equal to yours 2 into now I have to use a freehand tool because I have to mark the square root symbol. Your n minus 1. Fine. It is the good bisection bandwidth where p is equal to square root of n. And the next parameter, the conductivity, is also equal to 2. That means we need minimum to disconnect at least 2 nodes to convert that into the 2 different networks, and the node degree can be here 2, 3 or 4. I just show you this with the help of the diagram, and the cost of the network, that is equal to twice of n minus square root of n. Square root I have to do because there exists to simple. Now just trying to make the diagram for the 2D mesh here. Usually it is represented with a perfect circle. These all circle represents the node and the lines are basically connecting wires. Yes. Now see here, whenever you need to divide it into the two different networks, you need to divide at least two arcs. Only then it will be connected into the two different parts. The degree is 2, 3 or 4. Here see, when we are in the corners, the degree of the node is 2. Here it is the degree of the node is 3 and here it is 4. So any number of the degree can be there. Since usually what we take the degree of the your network as the highest degree, therefore in this particular mesh the degree of this particular mesh is 4. Now we next go over the special case of the 2D mesh that is known as the torus. Is also called as wraparound mesh. It provides the improved parameters as compared to the normal 2D mesh. The diameter, here it is the square root of n. And the bandwidth is equal to 2 into square root of n. And the wonderful thing about this is that is a connectivity parameter that is equal to the for, and the cost is 2 into the square root of n. Let us see with the help of the diagram, and it's a normal mesh, 2D mesh only, but the boundaries are also connected to each other. In examination, take care about this thing. When if you will ask about the only mesh, then we have to explain both the 2D mesh as well as the torus. However, whenever it is specifically asked about the 2D mesh or the wraparound mesh, then we go about any one of them. Here it is normal the 2D mesh. Now we shall convert that into the torus. We shall connect the extreme components of rows as well as the columns. Here we have connected the extreme rows. Now we'll connect the extreme columns also in the similar fashion. here now the degree for the each component is now 4, which was 2 here, earlier 3 here, but now it is 1, 2, 3, 4 for all the components everywhere, right? So I forgot to write here about the degree. So D is equal to 4 for your torus. Now we go for the next component, that is cube. We can say that it is the three-dimensional extension of 2D mesh. It is also called 3D hypercube. Usually we have made the boxes in our childhood. See here, just like this box, and after that I'm working to this one like this. This one is a very simple example of the 3D cube we usually make, and the critical parameters which are defined for your 3D cube or the 3D hypercube, you can also say it is that your the diameter is equal to 3 into cube root of n here. Earlier we were writing, so here we have to write 3. Fine. Cube root of n and your bandwidth is equal to it is cube root of the n square. Instead of n, it is a and the connectivity is equal to the 4, that means 3. It means we need to delete at least 3 nodes to divide this particular cube into the 2 different networks. Degree is equal to the 3, 4, 5 and even the 6. If you see, it has the 3 degree. All the corners have the degree 3. And if we go for the higher, which we will make the next one in the next experiment, here it will be the 6. Up to 6 we can go when we make the hypercube with more sizes. Here it's only the 6 sides are there. And the network cost is equal to versus 2 n minus cube root of n square, or the we can say n raised to the power 2 by 3. After the 3D cubes, we have to go for the 3 cube connected cycles. Here you will see how the degree has been improved in this hypercube. It is a special case of the hypercube only. There is a minor change that your each node of the cube has the 3 different nodes. That is known as the 3 cube connected cycles. Just trying to show you here with the help of the diagram. I'm just going to represent the nodes with the help of the circle here. This node is circle. I just got to represent you only two nodes having the three cubes. Rest it will be same as it the previous one. Like this, and this particular cubic cycle will be available here also, here also, here also, here also, here also, and here also. Right? And the next one yours is a completely connected network. In this network, every node is connected with rest of all the nodes. If you go like this, I'm just going in the four nodes network. See this line. This is connected with all three. Now if over this network is already connected here, I'm going to connect it with this, followed by this, and similarly it is here. Now you can see there is a direct path available from the one node to the rest of the node. Any number of nodes can be connected. It's not a big issue. Since every node is connected to each other, therefore the diameter of the node is equal to 1. However, the cost will be on the higher side. It is equal to n into n minus 1 divided by 2. And obviously degree of the node is equal to n minus 1, because you can see it is a 4, then there are the degree is 3 for all the nodes. Then we go for the n-dimensional hypercubes. It has not been covered till now, because 2D hypercube